Welcome to Chapter 5. We'll be talking about stereochemistry. This is our review slide from Chapter 4. And these are Newman projections. So we're looking at some acyclic compounds. What you want to be able to do to answer this question is to take this compound out of the Newman projection. So here we have on this carbon here, we have CH, CH3, CH3, and then we also have, so that's this one, and then the green we have coming off of the blue carbon, CH2, CH3, and then the back carbon would be this one, and that has a CH3 coming off of it. And then you can count your carbons, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, and then let's do the same with this one. And that would be that CH3 and that CH3. And then we'll go with the back carbon here. And then this CH2, CH3, and then this CH2, CH3. And then what I would do is I would do the molecular formula and see if they have the same molecular formula. So C8, 3, 4, 5, 6, 7, 8, H, 3, 6, 9, 12, 13, 14, 15, 16, 17, 18. Molecular formula here, 1, 2, 3, 4, 5, 6, 7, 8, 3, 6, 9, 12, 13, 14, 15, 16, 17, 18. So they do have the same molecular formula, so they are related, okay? And now I would do the naming, and that's also a nice review. So you find your longest chain, 5, 1, 2, 3, 4, 5. So this is pentane, and then we have substituents coming off of the 2 and the 3. So 2-methyl, 3-ethyl, pentane, and then this one here, 1, 2, 3, 4, 5, that's pentane as well. And that's 2-methyl, and this is 3-ethyl. As you can see, they're the same name. So these are identical molecules. And that's the kind of stuff you want to be able, problems you want to work on for your exam. All right, how are the following molecules related? So this is another example. So here you have this compound, and you need to get this Newman projection out of the Newman projection. So let's do this here, CH3, CH3, and then we'll go to the back carbon here, and then CH, CH3, CH3, and then we have this CH coming off of that carbon here, and that is your back carbon. All right, now let's make sure we have the same number of carbons, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So they both have C8, 3, 6, 9, 12, 13, 14, 15, 16, 17, 18. This is 1, 2, 3, 4, 5, 6, 7, 8. 3, 6, 9, 12, 13, 14, 15, 16, 17, 18. So they are related. They have the same molecular formula. But let's do the naming, see if the connectivity is the same. 1, 2, 3, 4, 5, that's pentane. And then we have 2, 3, 4, 2, 3, 4 trimethyl pentane. This is 1, 2, 3, 4, 5, that's pentane. And then we have 2, 3, 3 trimethyl pentane. So you see this is 2, 3, 4, this is 2, 3, 3. So these are constitutional isomers. That means they have different connectivity, but they have same molecular formula. Okay, we also did the chair conformation, so for the cyclohexanes as a review. So what you want to do here is I would take this and make it two-dimensional and then give it a name. So this is equatorial up and this is axial up, and they're connected to 1, 2, 3, 4. So you can make this methyl up, and then this would be up as well, this isopropyl. So this would be cis 1 methyl 4 isopropyl cyclohexane. And then this one would be, so this is axial up, so this is equatorial down, this is axial up. Sometimes you have to put in your axial hydrogens to see that that's equatorial down. And then let's do our two-dimensional drawing in this. Notice this is 1, 2, 3. So now we have equatorial down. So down will go back, and then axial up on the 3. So what is this? This is trans, and then this is 1 methyl 3 isopropyl cyclohexane. So these have the same molecular formula. You could work that out and you'll see. But they have different connectivity because they have different names, different numbers. Now, if they had been just a cis and a trans that was different, but the numbers of the connectivity were the same, then they would have been stereoisomers. Okay, here we go again. This is 1, 2, 3, 1, 2, 3. This is axial up, so that's equatorial down. So we'll make the methyl going down. And then this is axial up, 1, 2, 3. So there's that. And then let's do this one. This is equatorial up, that's axial down. This is axial down, so that's equatorial up. So we have up on the 1, 2, 3, and then we have up on the isopropyl. So this is cis dash 1, 3, or 1 dash methyl dash 3 isopropyl cyclohexane, and then this would be trans 1 methyl 3 isopropyl cyclohexane. And these, since they're same everything, same molecular formula and same connectivity, the only thing that's different is the trans versus the cis, and these are stereoisomers. And in this chapter, we're going to break down stereoisomers. That means they have the same connectivity, so they have the same molecular formula, but their orientation in space is different. Space differs. And you see that with this being below the ring, this is above, and this is above, and this is above. Their orientation in space is different. And in this chapter, we're going to break stereoisomers down even more. We're going to break them down into enantiomers. We'll talk about diastereomers. We'll be able to name, we'll do nomenclature. So I'll teach you how to sign R and S. This is called configuration. So when you have cis and trans in the name, so I'll go ahead and tell you that, that's a diastereomer. So those stereoisomers, because there's two, and dia means more than one. So welcome to chapter 5. We're going to do stereochemistry. So stereochemistry refers to the three-dimensional structure of the molecule, and this can create different properties. Starch and cellulose. So you know that we cannot digest cellulose, right? But we eat starch. Think of a potato. And that's because the sugars, the length for cellulose are a beta. It's called a beta glycosidic bond. And the starch is an alpha glycosidic bond. And alpha sugars, it's just an orientation in space. So that's the difference. They are different. Okay, constitutional isomers. We've talked about constitutional isomers. They have a different connectivity, but so constitutional isomers have the same molecular formula. They have a different connectivity. And that makes them different compounds. So they're going to have different physical properties, different chemical properties. Stereoisomers differ in the way the atoms are oriented in space. And so they're going to have identical IUPAC names, except they might have a different if they have a prefix like cis or trans, that's going to make them diastereomers. See the word stereomers already in there. They're always going to have the same functional group because they're going to have the same name, except for the cis and the trans. Different in configuration. Configuration, we're going to get even more specific, and you're going to assign R and S to the stereocenter. Now, the stereocenter is a carbon that is stereogenic. So this is the nomenclature for the carbons are oriented different in space. An example that we're going to talk about is your hands. So you know you have a right hand and you have a left hand. And did you know your hands are enantiomers? They're enantiomers of each other. Okay, so enantiomers in the sense of smell. So these are enantiomers of each other. You have S-carvone and R-carvone. So S-carvone and R-carvone, this is where the S is talking about this carbon here in the orientation, and you'll learn about how to assign S and R to these stereogenic centers. And this one is R. Now these might look the same because this is going back, but you'll see that this carbonyl is on this side of the molecule, whereas this carbonyl is on the other side. It's just like your hands with your thumbs. They're enantiomers. Well, your nose knows the difference because we have biological receptors, smell receptors, that are chiral. So chiral means there's an asymmetry aspect to it, and so chiral means that they well, your hands, it's handedness. Handedness. That's what chiral actually means. It's a Latin word for handedness. And so that means like your right hand, your left hand. And so caraway seeds have S-carvone. If you've ever tasted caraway or smelled caraway, it's very different than spearmint, which is R. So they're showing you here constitutional isomers. So this is an example of constitutional isomer. They have the same molecular formula, but they have different connectivity. The 3 versus the 2-methylpentane. They're going to have different boiling points and different melting points. Here, these are stereoisomers. They're both 1,2-dimethylcyclopentane, but one's cis because both of those methyl groups are on the same side of the ring. And then these are trans because they're opposite sides of the ring. These are diastereomers. And so, like I said, your hand is chiral And so if you take the mirror image, and this is actually what this is what you're going to have to do. Chiral means you take a mirror image. So step one, you take the mirror image. So you're going to have to draw the mirror image. So first of all, you're going to be drawing these molecules, and then you're going to rotate the mirror image that you drew. Okay, so that's drawn. And then you're going to ask yourself, superimposable or not? If it's non-superimposable, then that means it's chiral. If they are, if yes, that they're superimposable, meaning they're the same, then it's achiral. And A means without chirality. Okay, so here you would draw your mirror image, and the way you do this is you line this up here, and then you draw everything, and then you see your thumbs over here, your thumbs here, and then now you take this and rotate it. Okay, so and when you do your molecule with your hand, so hopefully right now you've got both hands looking at each other. Take your right hand and rotate it, and then wiggle your thumb. In fact, I will do this. I will make so this is, let's do that, and then here this will be this pinky, and then here this will be this thumb. So when this gets rotated, you see there's your thumb and your blue pinky. This is how you know that it's non superimposable. Your pinky, you don't even see your pinky, but wiggle your thumbs. And when you wiggle your thumbs, you're going to see that you have a thumb here and a thumb there. If they lined up and your thumbs were both on the same side, then it would be superimposable. And that's why your hands are chiral. They are non-superimposable. It's handedness. Now, so when you draw your molecule, so you're going to draw the mirror image, and then when you rotate, let's talk about rotate, how to rotate, because this is actually a hard concept and a lot of people have trouble doing this. So how to rotate. Now remember, you're only going to rotate the mirror image. So you draw the mirror image and then you rotate the mirror image. When you rotate the mirror image, top stays top, bottom stays bottom. That's important because a lot of people want to flip it. You don't flip it. Stops, the top stays the top. See these fingers? They're still at the top. You see this part of your hand? It's still at the bottom. Okay, it's still at the bottom. So the top stays as top, the bottom stays the bottom. But what was front, so if this is your front, is now in back. So front becomes back. Back becomes front. And whatever's on the left side goes to the right side. Whatever's on the right side goes to the left side. Now what you might have to do this for a two-dimensional, this front and back are dashes and wedges. Okay, so you might have to do the dashes and wedges. So remember that. That's how we're actually going to rotate the image. And then you'll have to see if they're the same. Socks are achiral. How do you know that? Okay, so here when you draw the mirror image, you can see that that's your heel and that's your toe. Okay, now when you rotate this, the top still stays the top. The bottom still stays the bottom. And what happens is this blue, and it looks like they rotated this one. They rotated this mirror image. So let's make sure it's kind of confusing. This is your mirror image that's rotated because you see how they have this orientation. So the top still stays the top and the bottom still stays the bottom. But now this is on the right hand side. And now you see how this is on the left. And then the toe part is on the left. Now the toe is on the right. And you see how this is superimposable. If it's superimposable, then it's chiral, achiral, achiral. They're identical. So water is achiral. So here if you take a molecule, remember the top will stay the top. So there's your top. And the bottom stays the bottom. But when you rotate it, this on the right becomes the left. And this on the left becomes the right. But since these are both hydrogen, they're going to be superimposable. So it's achiral. Now, this one, is this one chiral, achiral? Well, let's see what mirror image. Okay, so we're rotating this one. See how your book did the switcheroo? We're rotating this one. Now this is top. Top stays top. Okay, so there's your top. And now this is on the right. And so now it's on the left. And then this is on your left, the green, and it becomes on the right. And then when you compare this rotated image with your original, you see that they are superimposable. So that is achiral. That means they're identical. I mean, if it's achiral, you say, what's the relationship? They're the same molecule. They're the same compound. They're identical if they're achiral. So chiral molecules, if they are mirror images of each other, this is only if they're mirror images and they're non-superimposable. If they're non-superimposable mirror images, they are enantiomers. So let's look at this. So you have your original compound, and this is your drawn mirror image. Because you're going to have to draw the mirror image. Okay, it's drawn. So here you have the mirror image. Now you're going to rotate this mirror image. So this is your top. Here's your top, and you see this is there. Now what's on the right goes to the left, and what was on the left goes to the right. Now you'll see that these are not mirror images because the green is coming at you and the red is going back, and in the original the red is coming at you and the green is going back, and so that makes them non-superimposable. And if they're non-superimposable, they are, and they're mirror images of each other, they're enantiomers. So I can look at this molecule and say definitely has a mirror image, definitely are enantiomers. How can I do that? Well, you ask yourself, is the carbon bonded to 4 different groups? And I say groups on purpose because you're going to have to look at the whole group as a whole. So let's look. The carbon is bonded to a yellow, a red, a green, and a white. Okay, so the carbon is bonded to a hydrogen. It's bonded to, I guess that would be a fluorine. And see, that's in the plane there. So we call that the plane. What's coming at you is the red, which we'll call, it's the big one, so we'll make that bromine. And then the green would be Cl. Okay, so another thing to note, you need to always put these dashes and wedges on the same side, or else you're going to get your answer wrong. If you have this a single line, that's in the plane. Like, okay, look at a flat piece of paper. So what's coming at you is the wedge at you, and the back is the dash. Now, if you were to draw the mirror image of this, okay, so then you would draw the hydrogen, the carbon, and you would draw the fluorine, and you would draw the bromine coming at you. See if I can. So if you were to draw the mirror image, you would draw the carbon, the hydrogen, and then you see how the fluorine's there? So you would want to draw the fluorine like that, fluorine, and then you would draw the bromine like this, and the chlorine like this. Okay, so that's how you would draw the mirror image. So I kind of just look like if they were kissing each other here. Okay, the hydrogen, the carbon, the fluorine. And those all have to be on the lines. The mirror images are the same. So bromine has to be coming at you with a wedge, and the chlorine has to be going back with the dash. Now, this image here, we're going to rotate. Now remember the rules when you rotate. Okay. The top stays the top, the bottom stays the bottom. We're rotated up here for space. I can't erase that. And then what's in back goes front. Okay, so we're going to draw this like this, and now the fluorine goes that way. You see I have the lines here, but the fluorine was on the left here. Now the fluorine is going to be on the right. And then what was coming at you has to go in the back. So now bromine has to go in the back, and what's going in the back has to come to the front. So here we have chlorine here, and chlorine has to come here. So you see that chlorine is on the right, and now it's on the left. The fluorine was on the left, and now it's on the right. And the bromine was coming at you, now it's going back. The chlorine was in the back, and now it's on the wedge coming at you. If you don't believe me, take your hand, take your right hand with the thumb, wiggle your thumb. Now, that's the mirror image. Rotate it. Rotate your right hand. Your hydrogens are your fingernails. They're still at the top. Your thumb is now, instead of close to you, it's opposed. And your pinky is now closer to you. So that's what you do when you rotate. Now, what you're comparing this compound with the original. And so are they superimposable? Well, the H and the F are all the same, okay, because they're in the plane. But do you see that the bromine here is lined up with the chlorine, and the chlorine is lined up with the bromine? And because that's the way that is, these are chiral. And the carbon is bonded to 4 different groups. Okay, so we're looking for stereogenic centers. One of the things I want you to be able to do is I can determine or identify stereocenters or stereogenic centers or stereocenters in a molecule. And usually we'll indicate these in a big molecule with a little star by the carbon. Now this is important, if you only have one stereogenic center, you can go ahead and say, okay, that's always, remember anytime we say always, is going to be chiral. So if you have one You can have the other one, those can be enantiomers. If you have more than 2 or more stereogenic centers, it may or may not be chiral. Okay, so you're going to have to look and do some more investigation on that. So if it has a plane of symmetry, that's usually the number one place of investigation. If you have a plane of symmetry, then it's going to be achiral. So that's always, if there's a plane of symmetry. And you'll hear me say that, and that's especially if you have more than one stereocenter. If you have only one stereocenter, you will not have a plane of symmetry. So here you see the CH2, you got 2 hydrogens on that carbon. So you right now know that that's achiral. And so there's no plane of symmetry for this one, which only has 1 hydrogen. This one's achiral. And so if you have a carbon that's bonded to the same thing, it's going to be achiral. So when I look quickly for an asymmetric carbon, it's another carbon, it's the same thing, aka also known as a stereogenic carbon, I immediately pass over a CH2, which we call a methylene, a CH3, which is called a methyl, because those carbons are bonded to more than one of the same thing. CH3, that's a carbon bonded to 3 hydrogens. That's 3 of the same thing. A methylene, CH2, that's a carbon bonded to 2 things. A carbonyl, carbonyls, see? Carbonyl, that's a carbon bonded to oxygen, 1 twice, okay? That's an sp2 carbon. You're not going to have no stereocenters for an sp2 carbon. It has to be sp3. Why? Carbon must be bonded to 4 different groups. Okay, so add your superscripts, sp3. Carbon has to be sp3. That's 4 groups. So anytime you see something like this, you don't have to worry about a stereogenic carbon. That's an sp carbon. That carbon's bonded to 2 things. 1, 2. Okay, a carbon-carbon double bond. That's an sp2 carbon. So you're only looking for sp3 carbons. So the only ones you're going to see is a methyne, which is CH. It's also called a methyne. Or a carbon bonded with no hydrogens. So the summary of chirality, everything has a mirror image. Whether it's superimposable determines whether you have a chiral compound or not. If there's not a plane of symmetry, then they're chiral. If they are superimposable, they have a plane of symmetry, which makes them achiral. Stereogenic center and chiral molecules are related, but they're different. Distinct means different. A chiral molecule must have 1 or more stereogenic centers, so you have to have at least 1. Okay, which of the following contain a stereocenter? So in these, you want to go ahead and draw out your structures. A CH2. Remember I told you that's how you solve every problem. You don't use calculators, but you got to have Lewis structures. A CHCl3. So draw out your Lewis structures. CH3, CH2, C, 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 CH3, CH3. If you're having trouble with this, then you need to go back to Pogel 1. CH and then OH would be bonded to the H, the carbon, and then CH2, CH3. Now, do you remember I said I look for sp3 carbons, and they have to be either a CH or a carbon with no H's. So I'm going to definitely say no to an sp2 carbon. These are sp2. This carbon is a CH, methine, but it has 3 chlorines, so that's a no. These are CH3s, and a CH2, those cannot be. This is SP, and this is a CH3, so we don't worry about those. This is a CH3, that can't be, but look at this carbon. This is what I would call a methine, meaning it's a carbon hydrogen, and then what are the groups? It has a OH, and I say groups, it has a CH3, and it has a CH2, CH3. So those are 4 different groups. So this is your, you see I put the star, it is that carbon that is asymmetric. CH2s, we don't worry about CH2s or CH3s. So stereogenic centers. To locate a stereogenic center, you need to examine each tetrahedral carbon. So a tetrahedral carbon is an sp3 carbon, and look for the 4 groups that it's bonded to. Groups. Always omit consideration of carbons that cannot be tetrahedral centers. And omit, so that's sp or sp2 hybridized carbons, and omits methylene and methyls. So this is the stereogenic center here, because you have a hydrogen, a bromine, an ethyl, and a propyl. Okay, so here's a molecule in which there's multiple stereogenic centers. You will be given a molecule such as this, and you would be expected to locate the stereogenic centers. In this case, there are 2. You should see right away that these are all sp2 carbons. Those are all sp2 carbons, so they cannot be. So any of these aromatic rings are sp2 carbons. This carbonyl is an sp2 carbon, and this is a CH2, so that can't be. We have CH2s and CH3s. The only ones we're looking, that's a CH2. That's a CH3. The only ones we're looking at is this one here, and what are the 4 groups? This is one group, that's a phenyl. This is a phenyl, and then a CH2. So that's a different group. Here and here. So work on some problems. There's 3 stereogenic centers there. And do some example problems. So enantiomers are non-superimposable mirror images. And so I want you to be able to draw like the mirror image if you were given this compound here. Notice that the CH3 is on top here. And then I always, like I said, I think of them like kissing each other, okay? So what's coming first on this side is the hydrogen. And you got to make sure it's a mirror image. So if this has a dash, this needs a dash. And this is a wedge for the OH. This has to be a wedge. And see how they're the close ones? So you draw that way. And then you have the CH2, CH3 going back. Now, once you draw the mirror image, you have to rotate it. And how would I rotate this on my piece of paper? So everything that's on the right will go to the left side. So that's the first thing I'm going to do. I'm going to do CH3, and I'm going to draw the CH2, CH3. So this is on the right, and now it's on the left. And then what is front goes to the back, and the back goes to the front. So you see how I'm going to put a wedge here, and I'm going to put a dash here. And so right now we have the OH on the wedge coming at you. Now the OH has to go on the dash, and then the H has to go on the wedge because it was on the dash. So this is the rotation, and then I'm going to compare the original with my rotated one and see, are they superimposable? And so you see that this is on the same side and this is on the same side, but what's different is this OH is coming at you, this one's going back. So they're non-superimposable. And you should be able to tell that because this carbon is bonded to 4 different groups, a CH3, an OH, an H, and then a CH2, CH3. And you can practice that more. Okay, so we also want, what about in rings? What about cyclic compounds? They're a little more challenging. This is one chapter where if you did have model kits, that would be helpful for you. Okay, so let's see what we have. The same thing, you're looking, these are all CH2s, 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 CH2s. We don't worry about CH2. This is a CH3. Now you see here is a CH. So then you can say, okay, what's the groups? Well, okay, so you have an H. H is different. The CH3 is different. But are the other ones different? So you go out and you see they're the same. And I do this with my index finger. And then you go to the next one and you say they're the same. If you can go out with your index finger and you run into each other, they're the same. These are gonna, this is not a stereocenter, see? Because you can go out with your index finger, and I do one on each, and if the index fingers, because you have to work out, you go to the next carbon and the next and the next until you find a point of difference when you're doing a ring, okay? And if your fingers run into each other, that means there's no point of difference, no difference. So here, when we look at this, we're like, okay, that's a CH3. That's not, these are sp2 carbons, so they're not. So carbon number 3, that is a methine, so that has a hydrogen, and it has a CH3. And then, so now I'm going to go and go, okay, let's move out to the next one. Do you see that that is an sp2ch, and this is a CH2? That's a point of difference. So that's going to be a chiral carbon. That is a chiral carbon right there. Number 3 is, because you have a point of difference. Okay, so that means for these, if you draw the mirror image, you would draw the methyl going up like this. You would draw the H going down, and then make sure you have your top here, the double bond on the top, and then you've got your bond here. And then if you rotate this, how would you rotate that? You would have to, the top has to remain on the top, so you still got your double bond there. And then now the methyl would go down and the hydrogen would go up. And then these are the two you would compare. And that's what you would see is that these have switched. And once again, it's kind of like your thumb. And those are enantiomers because they have enantiomers by definition. The mirror image, everything has a mirror image, but the mirror image is not superimposable. And superimposable means when you rotate it and then you compare it with the original. The other thing, if you have a stereocenter and you have one, they are enantiomers of each other. Okay, so these are enantiomers. You have a stereocenter. Thalidomide. I actually did research in my 20s on thalidomide. Thalidomide was a drug in the 1950s. You can look it up. It was not given into America. It wasn't given into the USA. It was for morning sickness and it's for nausea. But the problem is it's a teratogen. A teratogen causes birth defects. So these children were being born with these premature limbs. So if you ever see someone, and you can actually go online and see these babies, and they have these hands that grow kind of, it looks like it's almost growing out of their shoulder, okay? Because the limbs never differentiated. And the reason why, and they didn't know this, but one of the enantiomers is an angiogenesis inhibitor. And what that means is it stops blood growth. Now, it's being used by Celgene as an anti-cancer drug. And it's actually a good anti-cancer drug, because you would want to stop blood development and blood growth to a tumor cell. However, when you're a placenta and you need blood and nutrition for a developing baby, this could be a problem. And so thalidomide is the asymmetric carbon is right here. But now, reason why this was a landmark case is was the first time we realized that drug molecules that are enantiomers have different biological properties. And so then a lot of drug companies started looking at the different enantiomers. And these are really hard to separate. I worked on a cancer drug for prostate cancer, and we had 3 stereocenters. Now, one other thing I want to say is, like, if you've ever seen albuterol versus Xopenex. So Xopenex is only a single enantiomer, and albuterol, you're going to learn this word, racemic. Racemic is R and S. They're both enantiomers, and it's a 50-50%, so they're not separated. Albuterol, these both open the airways, so if you have trouble breathing, my daughter had to take these medications like 3 times a day when she was little, breathing treatments. But albuterol will cause your heart to race. So it'll cause a racing heart. So a lot of times older people and younger children will give just the single enantiomer, Xopenex, which just opens the airways. So these are drugs typically given by respiratory therapists for asthma. Okay, so these are just showing you, so sugar has lots of stereocenters, folks, okay? Taxol, anti-cancer agent, has lots of stereocenters. This increases the complexity of a drug molecule when you have to synthesize that molecule. How many stereocenters in this molecule? Okay, hopefully you answered 1, okay, and this is it. So this is it has a hydrogen and a CH3, and then if you work your way out, those are the same, and then you get here, this is an sp2 carbonyl, and this is a CH2. So that's your point of difference. And so that means you have 1 stereocenter. If you'd gone the whole way, if you'd had something like this, then this would not, because you would work your way around, you go here, and then you go there, and then your fingers would meet, and that would have no point of difference. And so that would be 0 stereocenters. How many stereocenters in this? 0, right? Because this is an sp2 carbon, and then all the others are CH2s. All right, so now let's do the nomenclature. You're going to have to first locate a stereocenter. And then second, you need to name that stereocenter as either R or S. And so I will show you how to do that. When you assign priorities, so the first thing you're going to have to do is assign priorities. And this is based on atomic number. So you might want to get out a periodic table. When I was studying organic chemistry, instead of atomic number, we used atomic mass. You can use either way. This was important for like hydrogen and deuterium and tritium. D is the isotope of hydrogen 2. This is hydrogen 1, and tritium is H3. A lot of times you'll see radio labeling. You might see your homework where an H is replaced as a D. And this is just an isotope. It's the heavier isotope of hydrogen, so it has one neutron and one proton. You might even see it in some of these examples. Chemically, it behaves the same, but you can differentiate those. And sometimes that's like we do radio labeling. That's how we do the different isotopes. But that's where atomic mass is actually better. So I'm kind of shocked that they ever switched the scientists that decide that this is the way to go to atomic number, because in this case deuterium D would have a higher priority. Either way, but if you hear me exchanging atomic mass, it's because I'm old school. Okay, so obviously Br is going to get your higher atomic number, atomic mass. You can look at that on the periodic table. And then chlorine is going to be number 2. You see, you want to assign these. And then fluorine is 3. And then hydrogen's 4. Hydrogen is going to always be your lightest because it only has an atomic number of 1. Okay, rule number 2. On the stereogenic center, after you assign the priorities based on the atomic numbers, then, well, what if you have a tie? So here we have a carbon and we have a carbon. So obviously oxygen, you look at this, you've got to look at the direct element, folks. No shortcut on this. And so you're comparing oxygen, hydrogen, carbon, carbon. So oxygen is number 1, hydrogen is number 4. Now we have a tie between carbon, okay? Because carbon is the same. Now you got to look at what's this carbon, and you want to write it out. That carbon is bonded to 3 hydrogens. This carbon is bonded to a hydrogen, and a carbon. So do the tree thing, okay? And just go forward. Don't go backwards. Don't go backwards. So then you just look here, and you're like, okay, well, we got 3 hydrogens. This one wins. And the first time you find the one that wins from that carbon, you can go ahead and say, okay, that's going to be number 2, and that'll be number 3. And see, that's what they showed right here. So that's if you have a tie. If you have isotopes, that's what I was talking about with hydrogen versus deuterium, you go with the mass. Okay, so if you come out and you have a carbonyl, so you got that carbon, then you're going to have to say, okay, it's always going to be 3 because you're not going to count what it's bonded to in the past. So it's going to be that carbon's bonded to an oxygen, a hydrogen. So carbon is bonded to 2 oxygens. But then if you have that, then what's the oxygen bonded to? Oxygen is bonded to 2 carbons. So they're showing you that. So here, if you have this and you go this carbon is bonded to a hydrogen, a carbon, a carbon. This carbon is bonded to a carbon, a carbon, a carbon. And so 3 carbons is going to win. So a lot of times the double bond, triple bond, you just branch them out. All right, and so let's look at some of these. So they find that the stereogenic assigning priorities. So you need to be able to say, I can assign priorities on a stereogenic carbon, because you will be just given questions on that. So not only do you need to be able to locate a stereogenic carbon, you need to be able to assign priorities. So here bromine is number 1, H is number 4, and you got chlorine would be 2, and then carbon would be 3. Here, this one's a little hairier because they're all carbon. So you have here, number 1, this carbon is bonded to a carbon and a carbon. This carbon is bonded to a carbon. This carbon is bonded to a carbon. and this carbon is bonded to an H, an H, and an H. So this carbon is obviously the least, and since this red carbon is bonded to two carbons, it's number one. And then here we have these carbons are bonded to just one carbon, and so this carbon's bonded to one carbon. This carbon's bonded to one carbon, but this one is a carbon bonded to three hydrogens, and this carbon is bonded to a carbon. So this is going to be number two. All right, so looking at this stereogenic carbon, we have an oxygen, a hydrogen, a carbon, and a carbon. So could you just look at the elements? So oxygen is going to be number one, and hydrogen is going to be number four. And then so now we're looking at the carbon and the carbon. This carbon is bonded to an oxygen with three things, hydrogen and a hydrogen. This carbon, we'll make green, this carbon bonded to an oxygen, an oxygen, and an oxygen. So oxygen ties, but then we have two oxygens, and then we have two hydrogens, so this is going to be number two. All right, so let's assign our priorities. What's the correct order of assignments of priorities for the following? And the big mouth means the biggest, which is the highest priority. So number one in this case, and four would be the lowest priority. So hopefully you saw CH3 would be your lowest, and then chlorine's going to be your highest. And then you're comparing these two here. This is a carbon bonded to a hydrogen, carbon and a carbon. This is a carbon bonded to a hydrogen and oxygen. And so oxygen wins. So D is your answer. Okay, so how do we assign R and S? So once you find the stereocenter, and you see that this is an enantiomer of each other, the first thing you want to do is assign the priorities. So you need to assign your priorities. So number one, assign priorities. So you need to list them 1, 2, 3, 4. You'll never have more than 4. And then I actually do it differently than the book. The book kind of takes a long approach. So I take this and I assign this a priority. Okay, so oxygen's 1, I agree. Hydrogen's 4. We have a tie with a carbon and a carbon, but this is CH3 and this is going to bond to another carbon. So that's 2 and that's 3. So I agree with these priorities. Now what I do is I connect the 1, 2, 3. I connect the dots. Okay, so I ignore 4. Ignore 4. So I don't even look at 4 and I go, okay, where's my 2? I go from 1 to 2 to 3. Okay, now am I turning the turning wheel? I'm driving my car now. The turning wheel, the steering wheel. Which way am I turning it? Am I turning it clockwise, which is also right? Am I turning the steering wheel to the right? I am, okay? So that's R. If I turn the steering wheel counterclockwise to the left, it's S. And S I think of as sinister. Okay, to the left. But see, I'm turning it to the right. So that's the second thing. So number one, assign priorities. Number two, connect 1, 2, 3. And then number three, are you turning R or are you turning it to S? And then do your check. Okay? The check. What's the check? You have to ask yourself the question. Is number 4 lowest priority in the back? Okay, so if yes, then R would stay R, or S would stay yes. If no, then you got to do a switcheroo. And then R would become, and you'd see me do this, R becomes S. So since your lowest priority is in the back, R stays R. So this one's R. And you will see that the book actually redraws it and does a switch, which I think you'll find is time consuming and creates another opportunity for an issue for mistakes. Okay. So yes, you want to trace so this is one thing we agree with. Clockwise is R, counterclockwise is S. And so here we have our priorities 1, 2, and 3, and that is R. And since your hydrogen's number 4 and it's on the dash, so it's already in the back, R will stay R. Here, 1, 2, 3, and hydrogen's in the back, so S will stay S. No, so they're going through this thing. What if your higher priority is not facing towards you? Technically, this is where you could have models and you would actually take your highest priority and you would hold it in the back, and then you would connect your 1, 2, 3 priorities. And then of course that would be R, and that's really how you figure it out. But I'm showing you how to do it on a 2-dimensional. We're dealing with 3-dimensional objects, sp3 carbon. So the truth is, if I don't know the answer and I can't see it by doing my little tricks here where I put the switcheroo with the R in the back, with the lowest priority in the back, I will go and make a model, and I will literally take the lowest priority and put it in the back, and then I do the connection, because that's ultimately the correct answer. And in math and science, there is a correct answer. Okay, so what's the configuration of this compound? So the first thing you have to do is locate the stereogenic center. Do you see? There is not a stereogenic center. This is a CH3, CH3. That's the same. This is a CH2, so there's no stereogenic center. So you do not do configuration if there's no stereogenic center. Okay, what about here? Do we have stereogenic center? CH3, sp2 carbon, sp carbon, sp2. There is a stereogenic center. And so if you have the wedge there, you can go ahead and put in a hydrogen on the dash. If there is one, 1, 2, 3, 4. Okay, so that's a methine. And so that's number 4. So what's number 1 priority? Did you get this one? Because you're comparing a carbon, and a carbon. But number 1 carbon has a carbon, carbon, carbon. Okay, this carbon has a hydrogen, hydrogen, hydrogen. This other carbon here has a hydrogen, hydrogen, carbon. So this would be number 2, and this would be number 3 priority. So you have to assign your priorities once you find a stereogenic center. We're going to ignore the 4, and we're going to connect the dots. 1, 2, 3. Which way am I turning the steering wheel? Counterclockwise. Counterclockwise is left. The steering wheel of your car, you're turning left. That's S. And then you got to do your check. Okay, does S stay S? Okay. Is lowest priority number 4 in the back? Yes. So S stays S. If it wasn't, you'd have to do a flipperoo. So this is S. S is your answer. What is the configuration of the following compound? Do you have a stereocenter? Where is it? There's your stereocenter. A lot of times you put a little star there. Okay, what is not shown here? The hydrogen. Draw it in. Make sure you put it on the same side as the dash. All right, assign your priorities. That's going to be number 4. Fluorine is number 1 because you're comparing fluorine and a carbon. All right, so this is, we'll make that a yellow carbon. That's an H and an H and an H. This carbon is a carbon H. Okay, so this is going to be number 2. Number 2 priority. And this carbon then will be number 3. Now, we've assigned priorities. We're going to connect the 1, 2, 3. So to go from 1 to 2, I got to go this way. I'm turning the steering wheel counterclockwise. That is S. Did I do the other one right? I think so. Anyway, that is S, counterclockwise. I'm turning it to the left, counterclockwise. But, do your check. Is number 4 your lowest priority in the back? No. You see it's on the wedge? It's coming at you. So you're going to have to do a switcheroo. That's what we call a switcheroo. So S becomes R. So this molecule is R. Okay, what about a cyclic compound? Do you have a stereocenter? Is this a stereocenter? Well, let's do the check. What's not coming at you? 1, 2, 3 is the hydrogen. We'll draw the hydrogen in there. So it has a hydrogen, it has a CH3. These are the same, the CH2s. And then we have a point of differentiality. So you should at this point be able to detect that that's your lowest priority. And then here these are the same, but the red here would be a COO. So this is going to be priority number 1. And then this is going to be priority number 2. And then this will be priority number 3. So now we connect the 1, 2, 3. And so we connect the 1, 2, 3. 1, 2, 3, that is S. And then we do our check. 4's not in the back, so we have to do our switcheroo. So that should be R. All right, diastereomers. Diastereomers are stereoisomers. Dia means there's more than one stereocenter. How many stereocenters can you get? Technically, the number of stereocenters in a molecule is 2n. That's a formula. N is the number of stereocenters you find in a molecule. So if you have 2, then 2 times 2 is 4. And that's the most that you can be, the most that you can, 4 stereoisomers you can have. And we're going to have to learn the relationship to each other because that's what I can determine the relationships between compounds. Organic molecules, that's a learning objective for organic 1. Some stereoisomers will not be mirror images of each other. That means, so we're just going to have to see, though this is the formula for the max that you could possibly have, you will see that some of them have a point of symmetry. So this is where we're going to look at for symmetry. If there's symmetry, they are achiral. Okay. So finding all possible stereocenters, here you have to look and see. This can get confusing. So I do have a few things that I go by. One of the things I do is I assign R and S to the stereocenters. And that's what I do. So if you have a 2R and a 3S, then the enantiomer would be 2S and 3R. Okay, and the numbers are the carbon in which you're assigning your stereocenters. These are enantiomers of each other. If you have a compound that becomes 2R and 2R, well, what are these related to each other? These are diastereomers. And you got to make sure you don't have a plane of symmetry, which makes it confusing because then they would be achiral. So here the mirror image is drawn. I don't actually draw them out. I just assign R and S. And I do look for a plane of symmetry. So they're showing you that A and B are non-superposable, so they're going to be enantiomers of each other. So this is showing you how to do this with models. You can do it this way. I have some suggested problems in which I assign the relationship. They're showing you that A and B are enantiomers, C and D are enantiomers, A and C are diastereomers, A and D are diastereomers. These are so what would I do? Let me show you how I would solve this. I would go here and I would say, okay, we're going to name this 1, 2, 3, 4, 5, 5 pentane. So pentane, and we have that's 2, so we got 2 and 3 dibromo pentane, and then 2 and 3. And so this is where I'm going to number 2 and 3 as R or S. This is how I would solve this problem. So I would go with, this is number 2, carbon number 2. Okay, so let's first do carbon number 2 and sign the priorities. Hydrogen's going to be 4, bromine's going to be 1, this is going to be 2 because that carbon's bonded to bromine, and this is going to be 3. And I'm going to connect the 1, 2, 3, and I'm going to see that that is S. And then does S stay S? Yes, because hydrogen's in back, so S stays S. So that for A, compound A, this is going to be 2S. And then I've got to do the same thing with the next molecule, the next one, the 3. Okay, so this is 1, and this is 4 priority. This is going to be 3, and this is going to be 4. Oh, I'm sorry, this is going to be so this is going to be 2, and this is going to be 3, and I'm going to do 1, 2, 3, and that's R. Does R stay R? Yes, because hydrogen's in back, so R stays R, and so that's 3R. And so that is the correct configuration for A. And then if I was given compound B, I would do the same thing, and I'd make sure that this is the 2. You see, this is the 2, and so 2. And then I would be like 1 and 4, and this is 3, or this is 2, and this is 3, 1, 2, 3. That's R. R stays R because hydrogen's in back. And then I would do the same thing to find out what number 3 is. So here's number 3, carbon number 3. That's a 1 and that's a 4. This is going to be a 2 and a 3. So 1, 2, 3. That's going to be S, and S stays S. So that's S. Do you see that 2S and 2R are exact opposites, and 3R and 3S are exact opposites? That means they're enantiomers of each other. So A and B are enantiomers. Now what's C? Well, let's do 1, 2. So we're looking at 2. That's your 2. And then we have a 1 and a 4 and a 2 and a 3. So 1, 2, 3. That is S. But hydrogen is now coming at you, so S has to go to R. So that's 2R. And now we're going to do the other. This is carbon number 3. This is 1, and that's 4. That's priority 2 and 3. So that's R, and R stays R because hydrogen's in back. Okay, so do you see that 2R and 3R are not exactly opposites of these? Okay, so these are diastereomers. And also C would be a diastereomer of A. So A and C are diastereomers, and B and C are diastereomers. Because sometimes you might have to do the relationship between these two. And so the best way to do that is to do R and S. And if you go through the exercise, you would see that this is going to be exactly the opposite of this because they're enantiomers. So this is going to be 2S, 3S. Now the other thing you want to make sure is that you don't have a plane of symmetry, which you don't have here. So here you have 2 stereocenters. They're showing you that you can have 4. Now what you're going to see is these are the same group, and so that is, you're going to see that that could be a stereocenter. I haven't put in your, you might see this. And it's a way of, these are called Fisher projections. They're really good for sugars. Emil Fisher actually came up with a way to look at these stereogenic centers. These are called Fisher projections. You might have some of those because those were in the Wade book. It's a great way to look at these. What you do is you make one of these the top and the bottom, and this is your stereogenic center. But I can tell right now we're going to have a plane of symmetry when you convert this to this, and these is going to be called a meso compound. And meso are achiral because there's a plane of symmetry. When I get alerted to this is when I see that these are the same. And so this is the book's way of showing you the meso compounds. You draw the mirror image, and then you're going to do the superimposable rotation. And you'll see with models that they're superimposable because there's the plane of symmetry. So what you need to know is meso compounds have a plane of symmetry and that they're achiral. So meso, that means that they have a stereogenic center, but because they have a plane of symmetry, they're achiral. What that means is you're actually, maybe in your book it talks about it, I don't go into it in this curriculum because of time, but there's this polarimeter that rotates plane polarized light. So light gets shined through and you get one wavelength, and it'll rotate the light. When you hit a molecule that's chiral molecule, it will rotate light either right or it will go to the left. Right is considered D, S is considered S, no, left is considered actually L. So if you notice all your sugars that are natural, they also have this connotation D, and all your amino acids that make up your proteins in your body have L. And so this was before a lot was understood that amino acids, these are chiral molecules, and so our body has chiral molecules, and the L amino acids actually rotate this plane polarized light to the left, and sugars rotate them to the right. Well, actually, I'm not necessarily positive. Well, anyway, the whole point is when something's achiral, you get no rotation. You get zero. You can't get any measurement. And so if you have a plane of symmetry, you're not going to get any rotation of light. And that's the true experimental definition of whether a compound is chiral or achiral experimentally. And so what's the relationship between these? Since these are mirror images of each other, there's only going to be 3 compounds. And if you sign R and S, you'll see that if they're exactly RR, the other one has to be SS. Those are going to be enantiomers of each other. But if you have an R and an S, those are going to be diastereomers of each other. And then you just look for the plane of symmetry if there is one. So in this case, you're not going to have that because you have an ethyl. You don't have to worry about that. When I really look for it is when we have these cyclic rings. Um, so you have a cis. Cis is going to have a plane of symmetry. So you're going to have a meso compound there. This you do not have, no plane of symmetry. And that's what you're going to see. Um, these are going to be identical. So it's achiral. This it does not have a mirror image, so they are going to be enantiomers. The Fisher projections, this is what I was trying to show you. One way to do this is everything on this vertical is going back. And you can take your models and make it that way. And everything on the horizontal is coming on a wedge. We call that the bow tie. See how that's kind of a bow tie? And so this makes it, these you don't have to worry about symmetry because you see that the ethyl and the methyl are different. And so you're not going to have symmetry. But whenever these are, the top and the bottom are the same, you're going to have to look for that meso compound. Here, to sign R and S, you just sign your priorities just the same. So bromine's 1, hydrogen's 4, and this would be 2, and this would be 3. You connect your dots just the same. 1, 2, 3. That would be R. But then you'll see hydrogen is coming at you. So you're going to have to switcheroo. And so that would be R switches to S. And so Fisher, you would just see it written like this. But what you would want to do is then you would want to be like, oh, okay, the vertical is going back and the bow tie. And what's really nice about this is you can see whether you have a symmetry from the top and the bottom real quickly. And each, or these horizontals, are a stereocenter. And so when you have lots of stereocenters, you can quickly see symmetry and stereocenters. So this is a POGL that you can do and you can watch. I would say that probably MCATs and different professional programs expect you to know the Fisher projections, even though they're not in this textbook. So it's worth a 15, 20 minutes of your time. And this is just showing you, that was the other thing. This, if you can do Model 3, I think it'll be worth a question on your exam to do the assignments of these. So let's try. So draw the mirror image of the following. All right, well, let's do that. CH3, CH2, CH2, and then you put H and BR, and then BR over here and H. So that's the mirror image. How many stereocenters are in the following compound? This is a stereocenter and that's a stereocenter. So you can quickly see that there's 2. Okay, what is the configuration of the following compound? So this CHO is an aldehyde, by the way, and you use your highest oxidized state of carbon at the top, and this is a CH2OH at the bottom. So this has how many stereocenters? 1, 2, 3, 4. So you can see there's 4 of those. And then you would count, this is 1, this is 2, 3, 4, 5, 6 carbons. So that's a 2, and that's a 3, and that's a 4, and that's a 5. So if you want to know what this one is, you're trying to figure out what these blanks are. And so how do we do that real quickly? Let me get these numbers out. So we'll start with 2, carbon number 2. And remember, these are bow ties. So you can go ahead and just put that in there. Oxygen is going to be 1. This is a carbonyl. So that's going to be carbon O, carbon O. This is carbon O. So this one's going to be 2, and this is going to be number 3 because it's only one CO. This one's a double bond, so it's CO, and this is number 4. Then you connect your priorities 1, 2, 3. 1, 2, 3. What is that? That is turning this turning wheel to the left, so that's S. And then because hydrogen is coming at you on the bow tie, S becomes R. So this is 2R. And then we can go to the next one. Okay, so now we're looking at this carbon. This is going to be number 1, and this is going to be number 4, because oxygen is the direct bonded there. Now we have CO, and we CO. Okay, so then that's a tie, so we got to go out here. This is CO, so this is CO, and then it's also C. This one here is CO and CO. So you're comparing a carbon with an oxygen, so this one obviously wins. So that one's going to be number 2, and then this would be number 3. So now we're going to connect the 1, 2, 3, 1, 2, 3. So that's R, but this, remember, the horizontal's on the bow tie, so R becomes S. So this is 3S. All right, let's go to the next one. Okay, so we're here, and we're assigning priorities. So this is going to be number 1. This is going to be number 4. Now we have CO, CO, so they're the same, tie, and then we have CO. This is CO. This is CO and CH and CH, but this one goes to CC. So this one's going to be number 2, and this will be number 3. So now we connect 1, 2, 3. That is S, but remember hydrogen's on the bow tie, so S becomes R. That's 4R. And then we have our last stereocenter. And this is number 1, this is number 4, and this is CO, this is CO. But then we come up here, we have another CO, and this kind of goes to a dead end. So that's number 2, that's number 3. So 1, 2, 3 is R. And then because hydrogen's on the bow tie, that's going to be S. So 2R, 3S, 3S, 4R. Okay, did I mess up here? Let's see, we got 2R. We have 3S, we have 4R. So let's see, let's do this one again. It might just be if something like that happens, we'll make it a fill in the blank. That's a 1. That's definitely a 2. That's a 3. 1, 2, 3. That's S, but then it becomes R. So my bad, that's S. Turning left becomes R. So this is right. B is right. Okay, so this is a summary of the different types of isomers. Remember, isomers have the same molecular formula, but they're different compounds. So what kind of isomers can you have? Well, we've run into constitutional isomers, and so if the connectivity is different, and the connectivity is like the numbering, like of your substituents. If the numbering is all the same, but they're just different in the 3-dimension, we have a stereoisomers, and stereoisomers can be enantiomers, which are non-superimposable mirror images. You're going to have enantiomers of each other if you only have one stereocenter, for sure. And diastereomers, you're going to have more than one stereocenters, and these are not mirror images of each other. So you can look at these slides and kind of, this might help you with your flow chart and your decision making. Optical activity, like I said, we're not covering this. I've pulled this, but you can read this on your own if you want. If you worked with enantiomers, you would use a polarimeter to measure the rotation of plane polarized light. If these are important things, though, I will say that you will need to know. A compound is optically inactive if it does not change the polarization of light. Okay, and so an achiral molecule is optically inactive. Another optically inactive is if you have a racemic mixture, which you do need to know that. A racemic mixture is a 50-50 R and S enantiomer ratio. And so if you do have a compound in there that rotates plane polarized light, the analyzer will see that the direction of light has changed. It's not really, they do dextrorotary and they'll do positive. That's what you get with your sugars. And then R is negative. I mean, L is negative. These are not correlated with R and S. Sometimes you get compounds or questions like that. R and S is just a nomenclature in which we give names to. This is D and L. D and L are experimentally related to a positive rotation, which is clockwise, and negative rotation, which is negative, which is counterclockwise. This is experimentally determined. D does not necessarily mean that they're going to be R. L does not mean that S. You have to experimentally determine D and L, and then you have to determine absolute configuration. And that's what they're saying here. Racemic is optically inactive. That's important to know. The rotations cancel out each other. So the melting points and boiling points can be a little different if it's racemic. Usually you can't separate melting points and boiling points. Only optical activity can be separated for an enantiomer. So if we're talking about enantiomers, you can't separate them, but optical activity can. Biological receptors can distinguish. You have to have a chiral molecule to interact with a chiral receptor. We don't have to do the math on this. If you do need this in the future, you do have some suggested problems that could help you with that. And that's enantiomeric excess. We're not going to do that. This is the formula if you do need it. You have those slides available to you. This is just good to show you that A and B are enantiomers, so you can see that their melting points are the same, the solubility is the same. Their optical rotation is equal in magnitude but opposite in direction. And there's your designation. The C is a diastereomer, and you see it's going to be different. 146, 125. So it has different chemical properties. Diastereomers can be separated. They're just showing you different single enantiomers in different drugs. So the antidepressant is the stereocin or R. The ibuprofen is the S enantiomer. Naproxen, the S enantiomer, has the anti-inflammatory agent. Unfortunately, the R enantiomer is a liver toxin. And we've already talked about carbone. And this is your nasal cavity in which your brain can send olfactory nerve cells and distinguish between these molecules because the receptors have a certain shape that can fit just like your hand in a glove. That wraps up stereo specific chapter 5.